As a general rule, if you're going to have moving game objects in your game, you should make sure that they are rigid body objects. Rigid bodies are components that allow a game object to be affected by physics. They allow the object to fall under gravity and have physics properties such as mass, drag, and velocity. When we add a rigid body component to a game object, we often then refer to it as a rigid body object. The rigid body is required for any physics-based interaction, and the game object must also have a collider attached in order to interact with other physics objects. Without a rigid body, our power cube will simply hover in mid-air. But let's see what happens when we add one. Like any other component, it can be added using the Add Component button at the bottom of the inspector, or from the Component top menu. You'll find it under the Physics section. Now our object falls under gravity and can be controlled by the physics engine and any forces applied to it. Rigid bodies have numerous options. Firstly, there are settings to control the mass, drag, and angular drag of the game object. The mass of the object affects how collisions are treated with the object. Game objects with a higher mass will react less when collided with a lower mass game object. The drag of a game object affects how quickly it will slow down without other interactions. Think of it like air resistance. It's used to determine the rate of a loss of linear velocity. Similarly, angular drag affects how quickly the game object will slow its angular velocity, i.e. how fast it's rotating. So for example, if you're adding torque to the object to rotate it, the angular drag will create resistance to this force. The next option is whether or not the game object is affected by gravity. By enabling this checkbox, we use gravity. Settings for gravity can be seen in the Edit, Project Settings, Physics area of Unity. As you can see, it's a three-dimensional vector, which by default has a real-world value of -9.81. Because you can customize it globally here, you could also create interesting effects, such as low gravity for a platformer, or even setting it to a different axis as part of a puzzle game. For example, let's add gravity to the z-axis by a value of 5. And now the power cube is pulled towards the global z-axis. The Kinematic Setting affects whether or not a rigid body will react to physics. Ordinarily, when a scene begins, all static geometry, meaning any non-rigid body objects, are checked once by the physics engine, and not checked again for efficiency. However, when you move a static object, the physics engine must recheck all other static objects for the sake of accuracy, and this can be expensive to performance. To avoid this, kinematic objects can be used and moved via their transform by using the translate function. This means that you can have physics objects that affect others, but are not affected themselves. An obvious example of this would be the paddle in a Pong or Breakout style game. In this example, our rigid body power cube has use gravity checked. When we press play, the object falls to the ground. We also have our round prop summerflange object, which has a similar setup. If the power cube does not have gravity, then it will not fall under it, but it will be affected by other objects. If we don't want it to be affected by other objects, we can use isKinematic. And as stated, we can also move the object via its transform. So we'll make use of this simple script, which uses the translate function to move it via its forward direction every frame. And as you can see, the object still interacts with the others, but remains a rigid body, so is constantly informing the physics engine of its location, and not forcing the physics engine to re-evaluate the entire scene. The Interpolate and Extrapolate settings are there to solve jittering. If you experience slight movement of your object when moving it via a rigid body, use the Interpolate setting in order to smooth the transform movement based on the previous frame, and the Extrapolate setting to smooth based on a predicted next frame's location. The next setting is for type of collision detection. We have discrete, continuous, and continuous dynamic. The default is discrete, and unless you have any problems, you should use discrete. Continuous is for fast-moving objects that are interacting with static geometry, and continuous dynamic is for fast-moving objects that are interacting with other dynamic objects. Finally, the constraints section of the rigid body component allows you to constrain movement or rotation of the object by physics. For example, if you had a Tetris-style game, you might not want the cubes of your game to rotate as they fell into place. You could constrain this using the rotation constraints here. In this example, our power cube is falling onto the workbench. It's a rigid body that has use gravity checked. And as standard, it falls like this. If we didn't want it to rotate as it falls, we can freeze the rotation within the constraints. And now when it falls, no rotation occurs.